Welcome to the Learning Pines YouTube. We hope this video helps.
You start by defining geometry and constraints. Get nodes, members, and supports into a single coordinate system so math is consistent. Next, apply loads exactly where they act point loads at nodes, distributed loads converted to equivalent nodal loads. Once done, pick the analysis type: linear static for small deformations, geometric nonlinearity for large displacements, or dynamic for time effects. Make sure material properties and cross-sections are assigned before you assemble the stiffness. That prevents avoidable rework later. Form each member's local stiffness, then rotate into global coordinates using the transformation matrix. This aligns axial and bending responses. Once done, assemble the global stiffness K by summing member contributions at corresponding DOF. Apply boundary conditions by partitioning or modifying K and F. Make sure to remove rigid body modes. Then solve the reduced linear system. K reduced times displacements equals F reduced. For large models, use sparse or iterative solvers for speed and memory efficiency. And verify convergence with displacements known, compute member deformations and internal forces. For axial-dominated trusses, use N equals EA/L times axial extension. And for framed members, calculate bending and shear as needed. Once you have reactions and stresses, check allowable limits, buckling for slender members, and factor of safety. If results look off, run a mesh refinement or smaller load steps to isolate nonlinearity. Troubleshooting tip: if unstable modes appear, inspect supports and connectivity. Removing a zero stiffness member or adding a constraint usually fixes rigid body motion.
Thanks for watching. Consider subscribing if we helped you.